Okay, so oh, it's not sharing. Okay, so welcome to Math 409. This is problem solving. And so what I want to do today is talk a little bit about some proof techniques. And so, again, has everybody here seen proof of induction? All right, so I'm going to assume everybody is comfortable enough to speak up in public. Is there anybody here who has not seen proof by induction? Okay, so I'm not going to bother going through the standard proof by induction stuff. Let's just do more interesting stuff. All right, I can prove either everybody in the world has the same name or every number is a perfect square. Which would people like to see? Everybody has the same name or every number is a perfect square?
Perfect square.
Perfect square. Any other votes?
Yeah, perfect square.
Perfect square. Okay, so every positive integer is a perfect square. All right, so it is interesting. Somehow when I restart the class, it always changes the font size of the marker. Okay, so we're going to prove by induction. So Pn is any sum of n squares is a square. Does everybody agree that if I can prove every sum of n squares is a square, then I can prove every integer is a perfect square? Why is this enough?
Every integer is n times 1.
Good. So suffices as n equals 1 squared plus ... plus 1 squared. So all I have to do is, we're proving by induction that every integer is a perfect square. Every positive integer is a perfect square. And so we're going to prove by induction that any sum of n squares is a square. Okay. And this suffices because I can write my number n as 1 squared plus 1 squared plus 1 squared plus 1 squared. So base case, does everyone agree P1 is trivial? If I give you a square, it's not hard to prove that a square is a square. Yes? So now inductive step. Assume pk is true, prove pk plus 1. So we have, say, x1 squared plus xk squared plus xk plus 1 squared. And we have to show that this is a perfect square. Well, by induction, we know the last two is a perfect square. So xk minus 1 squared plus, I'll call this x squared. And then so this is by induction. And then by induction again, this just collapses. We're done. So every positive integer is a perfect square. What's wrong with this?
Where you made the parentheses, you can't assume that because it's not in accord with the inductive hypothesis.
Why not?
Because the subscript is k plus 1, and you're assuming it for less than k. Right?
Yeah. So let's say k is 50, then k plus 1 would be 51, and I'm just using it for 2. 2 is much less than 51.
Yeah, I think that the inductive step only works if k is critically greater than the word.
Yes. Yes. So this is what's going on. Here's k equals 1. Here's k equals 2, k equals 3, k equals 4. There's a gap. So if we knew the sum of any two squares is a square, then yes, it would collapse down. So the problem is if I give you, say, k equals 1, we would have x1 squared plus x2 squared And when I try to collapse things, there's nothing to collapse. And then when I try to then collapse, I would just get back to what I had, x1 squared plus x squared. And then when I try to collapse that, I can't because I only know it's true when k equals 1. I don't know it's true when k equals 2. This is the same thing as if you try to prove everybody in the world has the same name. You choose one special person and say, if I have a group of n plus 1 people, the first n all have the same name, the last n have all the same name, person 2 is in both groups. Well, if k equals 1, there is no person 2 that's in both groups. You have the group of just the first person and the group of just the last person. So a lot of bad proofs by induction implicitly have you assume something about the k, that k is large. This is the most common mistake people make in doing proofs by induction. You have to make sure that what you do works for all values of k. Frequently, it's the beginning that is a challenge. Okay, so everybody knows the sort of Gauss and adding the numbers from 1 to 100? We didn't do that in this class, right? Okay, that came up in my operations research class. So we have a beautiful, I'll call it S1 of n is 0 plus 1 plus 2 plus ... plus n. It doesn't matter if we start with 0 or we start with 1. I don't know if people have a preference. So Gauss had this beautiful proof. The story is the teacher was just having a really bad day and wanted to shut the little kids up and said, add the numbers from 1 to 100, expecting to have some time to just mentally recharge. And Gauss blurts out 50-50, immediately, in German, of course. And the solution is just add the numbers in reverse order. And when you add like this, you get twice the sum. And now each of these sums is n. And how many of these sums do we have? 100, or in general, we have not 100. Very careful. So if we're summing from 0 to n, and then we sum from n to 0, how many sums do we have? Well, I'm doing in general n. How many sums? We have n plus 1 sums. So this is going to be n times n plus 1. So S1 of n is just going to be n plus 1 over 2. You can also prove this by induction, or prove by induction. What is the difficulty in proving this by induction? Is everybody comfortable if I asked you to prove this by induction? You're fine? Okay. What if I give you S2 of n is 0 squared plus 1 squared plus n squared? It turns out that there is a polynomial formula for this as a function of n. Can anybody prove this by induction? Ah, so needy. You should have some initiative, right? Yes, if I was kind and I gave you the formula, would it be a very easy proof? Yeah, if I gave you, I want the sum of cubes or fourth powers or fifth powers. If I give you the formula, you just have to do some elementary algebra and just plug in and show that it works. So if I give you the formula, it's easy. The algebra may not be enjoyable, but it's easy. What if I don't give you the formula? So the conjecture is that, let's say SD of n, which is 0 to the d plus 1 to the d plus ... plus n to the d, is a polynomial in n of degree. Anybody want to guess the degree? I'm sorry? Not n plus 1, d plus 1. And leading coefficient, 1 over d plus 1. And this is it's approximately the integral from 0 to n of x to the d dx, which would then be n to the d plus 1 over d plus 1. And in fact, we can do even better. We can even get the constant term. And constant term is what? 0. Because if you take n equals 0, the sum is 0. So the constant term has to be 0 if it's a polynomial. So before I even go into detail about trying to figure out what it is, I have a decent conjecture. I believe it's going to be a polynomial of degree d plus 1. I think that the leading term is going to be 1 over d plus 1. I think the constant term is going to be 0. So for example, if I give you, say, anybody know the formula for S3 of n? Yes.
S1 n squared.
It is S1 n squared, which is a beautiful result. So it's going to be n squared, n plus 1 squared over 4. Okay. Anybody know the formula for S24601? Yeah. There are formulas for it. They involve Bernoulli numbers. Yeah, there are formulas for them. What you can do is the following. Interpolate. So gather data. Again, one of the themes of this class is to talk about how to attack a problem. Frequently, you're not going to have all the facts that you want. Well, what can I do to get the facts that I need? So you said it would be really easy if I was a nice professor and gave you the formula. I want to make sure well before the drop period that everybody knows I am not a nice professor, so that there's no false expectations for those of you who stay. So what could we do? Well, we think S3 of n is going to be a polynomial of degree what? 4. And so if we wanted to, we could even use our thoughts, and we know it's going to be 1/4 n to the 4th plus a n cubed plus b n squared plus cn. And I'm making my life a little bit easy because I'm using the analysis we did before. The leading coefficient has to be 1/4. Otherwise, it's not going to match up with the Riemann sums. And I know the constant term has to be 0. If I didn't know this, I would have to have 2 more coefficients, and I would have to do a little bit of additional work. This is a general rule of problem solving. Spending a little bit of time in the beginning thinking about things is often worth it. How many of you have ever watched these reality shows where they have people competing for things and you have so many minutes to either bake this or build this or whatnot? It's always interesting to see how much time do people spend planning before they just rush off because they're so worried of how much time they have. It's often very valuable to just spend a little bit of time and think. So can you calculate what S3 of 1 is? 1. S3 of 2. Okay, so you've got so you are correct because it is 8 or 9. Can you collapse? 9. So we're just adding 8 to this. And then the next one, S3 of 3 would be, have to add 27. So we get 26. Do we need any more? Oh, 36. And then S4, I'm sorry. So S3 of 4, now we have to add 125. So 150, 61. Did I do it properly? Oh, sorry. So we added 1 squared, 2 squared, 3. Oh, we're adding 4 squared. So we're adding 64. Sorry. So 60. So it's 100. So now we have 4 values. And so if you look at what's going on, if I put in, oh, wait a minute. We only had 3 coefficients. I didn't even need to do all of this. I have A, B, C. When I put in 1, this is where it gets a little bit annoying. Do I want to actually include the extra stuff for the coefficients of the 1/4 and the CN? I'm just trying to solve my equations in terms of what do I need. And so I'm just trying to think of what's the best way to write things down. So we know when we take A, B, C, when we take n equals 1, we get 1, then 9, then 36. And just trying to figure out what these A, B's, and C should be. And so what I would do is I would do maybe 1 minus 1/4, maybe 9 minus, so I have 2. So I'm just subtracting off the 1/4. So I'm basically saying an cubed plus bn squared plus cn equals s3 of n minus n to the 4th over 4. And if I do it like that, I can now write this as a really nice matrix equation. So now when I take n equals 1, I've got 1 cubed, 1 squared, 1, so it's just going to be 1, 1, 1. When I take n equals 2, I'm going to have 8, 4, 2. When I take n equals 3, I'm going to get 27, 9, 3. And then what do they equal? The first is 1 minus 1/4. So that's going to just be 3/4. The next is going to be 9 minus 2 to the 4th over 4. Well, 2 to the 4th over 4 is just 4. So this should just be 5. And then the last one is going to be 36 minus 81/4, I think. I have no desire to do the algebra. And now we have a way to find A, B, and C. So invert yields A, B, and C. So if I don't give you the formula, you can actually find the formula. If I didn't know that the leading coefficient was 1/4 and that the constant term was 0, I would just have a 5 by 5 matrix. I would just need more pieces of data before I could figure out what the formula is. But by knowing the structure, this allows me to trim it down a lot. What question might you ask about this matrix?
Singular.
So is this matrix singular?
Probably.
If it's singular, we have a problem. Potentially. So here's an interesting question. So if I give you the matrix, I'm going to look at the transpose of the matrix. Is that okay with everybody? So if I give you, say, alpha squared, ... Let's do alpha 1 squared, alpha 1 to the d, alpha 2 squared, ... alpha 2 to the d, ... And then we'll have alpha d squared, ... alpha d to the d. I want to know if the alphas are distinct. Is this invertible? That's the situation we have, right? So this is a very special matrix. Does anybody know the name of this matrix? It is the Vandermonde. How many people have ever seen the Vandermonde matrix? Okay, do you know how to calculate the determinant of the Vandermonde matrix?
The product of the differences of between alphas where the indices go. Like, okay, the product, say, with over an indices j and k with 1 less than equal to j smaller than k.
Okay, so it's going to be related to the product 1 less than equal to I, strictly less than j, less than equal to d of alpha I minus alpha j. So let's see why it starts off like this. the first thing is, if two of the alphas are the same, what must be true about the determinant? It's 0. Because if two of the alphas are the same, then you have two columns that are the same. So we know that whenever alpha I equals alpha j, the determinant is 0. So it has to be a multiple of this. So it's got to be this times something. What is the degree of this product? So how many indices do we have I and j between 1 and d that are distinct? It's d choose 2, which is d minus 1 over 2. If you think about what's going on when we multiply everything out, I'm hoping we did not make a mistake here. So what would be the degree when you multiply everything out? You have to choose something from each row. So you have something of degree 1, something of degree 2, something of degree 3. I'm actually getting the degree is d plus 1 over 2. So if we normalize things incorrectly. Oh, we have. We go up to d minus 1 if we want it to be a square matrix, I think. No. Or do we start off at 1? Is the first row all 1s? I think we start off with 1s and the first row is all constants. I think we start off with alpha to the 0. Okay, and then if we do this, that will now give us something of degree d. Okay, there we go. So sorry, off ever so slightly. So now, how do you form a determinant? You take one entry from each row in each column. And so if we look at it, everything in the first row has degree 0, everything in the second degree 1, all the way up to the last row, which has degree d minus 1. So the degree here is 0 plus 1 plus d minus 1, which we just showed a moment ago is d minus 1 times d over 2. So they have the same degree. So they have to differ by a factor that does not depend on alpha. And so the factor, it turns out to be either plus or minus 1, depending on how we're doing things. Normally, I think we do the larger index. So if I switch and do, I think, the larger index minus the smaller index, so factor independent of the alphas. Now, the most important thing is that we want that factor that's independent of the alphas to be anything other than 0. The only way we lose is if it's 0, because then it is a singular matrix. In fact, it's always a singular matrix then. So the question is, it would be wonderful to prove exactly what it is. It's going to be plus 1. But if we can't prove it's plus 1, can we just prove that it's not 0? Well, the nice thing is, since the answer is independent of the alphas, I only have to evaluate this for a very special case. And so we can do an extreme case. And this is one of the things I love to do. So extreme case. Let's choose alpha 1 is much less than alpha 2, is much less than ... is much less than ... is much less than alpha d. So imagine, alpha 1 is 1. Alpha 2 is a googolplex. Alpha 3 is a googolplex to the googolplex. Alpha, and so on and so on and so on. The numbers are going to be so astronomically larger than the previous. If you wanted to calculate the determinant, can anybody approximate what the determinant would be in terms of the alphas? When you look at all the different expansions, what would the determinant be approximately? So if I give you a 2 by 2 matrix, it's AD minus BC.
Is it just alpha 1 to the 0 times alpha 2 to the first power?
Yes.
And just the diagonal?
It's just the main diagonal. So it's approximately the main diagonal. And so if we choose the alphas to be so much larger than the previous, then the largest contribution is going to be from the main diagonal. And then when you go through and you do the algebra, you'll then see that it's going to be, I think, a +1 that's going to come into play. The main thing you see is that it can't have a zero determinant. It's enough to see that. You know, to see exactly what is the constant of +1. That's a little bit more work. You know, you would have to just go through and figure out the main term. But this is enough to show that it's not zero. Okay. So again, trying to show, you know, different proof techniques. What do we actually need versus what do we want? I will risk asking how many of you remember multivariable calculus? How many of you remember that you took multivariable calculus? Okay. Lagrange multipliers. Do people do Lagrange multipliers? So you use Lagrange multipliers to do constrained maxima. I have to lie on a surface and I want to figure out, you know, where is my maxima, minima candidates, and then I'll compare them. Okay. At the end of the day, do you care what lambda is when you're doing Lagrange multipliers? No. Lambda is meant to help you find your point. You might actually compute what lambda is, and there's actually a geometric significance that's telling you how fast maybe things are moving. But at the end of the day, you only care about the point. You only care about lambda as it helps you get there. And a lot of times when you're doing these Lagrange multiplier problems, you look at ratios and the ratios happen and the lambda cancels. Does this sound vaguely familiar? So again, it's always think about what do I actually need? And so here, all I need is that this is not zero. I just need to prove that this is invertible. Now, of course, you know, when we do this in a specific instance, we actually have a matrix that we can write down and check and see, is the matrix going to be the zero matrix or not? Okay. That means the matrix is going to have zero determinant or not. All right. So there was an interesting remark made that it turns out S3 is S1 squared. That's very unusual. And then there's an interesting question about just how generally does this hold. So one way of proving things, you know, is, you know, we can prove things by induction for these power sums. We need to know the formula to do it by induction, but with a little bit of work, we can sniff out the formula. So let's look at S3n, which is going to be 0 cubed plus 1 cubed plus 2 cubed plus n cubed. Okay. How would you prove that this is equal to S1 squared? So is it basically you just prove by induction that that formula works? Yes? So there's a lot of times in math where you can, you know, do a proof, but not necessarily have any intuition on why it's true. So let's think about what's going on. Let's think about what sums we know. Well, let's look at S1n squared, which is going to be the sum, k goes from 0 to n, of k squared. So let's write this as maybe the sum, k goes from 0 to n of k times the sum, m goes from 0 to n of m. And we know that this is going to be n squared, n plus 1 squared over 4. You know, we'll assume we know what S1 is. We've calculated that. So now we have to understand the sum of k times the sum of m. I can write this as a sum, k goes from 0 to n of k squared plus twice the sum 1 less than or equal to k less than m less than equal to n of k times m. Why is that true? Yes.
You're splitting the indices m and k where they're equal. You have the left determinant when they're different.
Right. So when I multiply everything out, I have all these different cross terms. I have the situation where the same term here hits the same term here. And then I could have maybe 2 hits 5, but that's also the same as 5 hits 2. And that's why I have a factor of 2 that I have to double count. I just order it so I have the small and the large. Okay. So now I want to do the sum of k times m. Any thoughts as to how I would do the sum of k times m? 1 less equal to k less equal to m. So let's write this more carefully. This is the sum, k goes from 0 to n of k squared plus twice, and let's write it as a double sum. So which do you want to do first, the sum on k or the sum on m? So that means you're going to fix k, and m will run from k plus 1 to n. So that's one possibility, is we could fix k, so k is going to go from 1 to n minus 1, and m is going to go from k plus 1 to n. How else could we do it?
Yeah,
the other way, I would much rather start off with a small value, and I just was starting off at 0, not at 1. So I would much rather start off with a small value than a large value. So we can just erase everything. And so I think it's easier to do the k sum first. Oh, sorry, this should be a 0. So k goes from 0 to what? M minus 1. And what's the range for m? 1 to n. And this will be k, and I can pull the m outside the sum. Okay. What's the sum of k from 0 to m minus 1? So what would be the sum of k from 0 to m minus 1? So it's m minus 1 times m over 2. And this is equal to n squared, n plus 1 squared over 4. And now, if I do this properly,
there is x squared in the second sum.
Thank you. And that m squared is going to be very important. So take 2. Okay, so we have the following. So this is the same as the sum, k goes from 0 to n of k squared. What's the first thing you notice in the next sum?
Oh, yeah, that does cancel.
The 2's cancel. So I'm going to have a sum, m goes from 1 to n of m cubed minus m squared. N squared, n plus 1 squared over 2. Now, when I'm summing from 1 to n, could I extend the sum to be from 0? Over 4, thank you. Fortunately, 2's can be changed into 4 with my terrible handwriting without too much trouble. So we can extend the sums to be from 0. And so this is the same as the sum, k goes from 0 to n of k squared, plus the sum, m goes from 0 to n of m cubed, minus the sum, k goes from 0 to n of k squared, equals n squared, n plus 1 squared over 4. Because it's a dummy variable. And now what do you notice? The sums cancel. And it yields the sum m goes from 0 to n of m cubed is n squared, n plus 1 squared over 4. So I love this proof because we actually bypass the sum of squares and get the sum of cubes next. And a lot of times in mathematics, AMS has the shirt where somebody's at the blackboard and they write, and then and then the miracle occurs, and you have this remarkable simplification at the end. And so it turns out that there's a general phenomenon going on. And so I've put a link to a paper I wrote with a colleague of mine on the sum of kth powers in terms of earlier sums. So you can actually represent everything in terms of just the sums of the first and second powers. And there's beautiful formulas for this. And there's lots of wonderful games you can play. Very elementary paper to look at. And again, the purpose of this is to just emphasize, really look at all the different stuff that's going on. Just because you've looked at something doesn't mean you've looked at it recently. And a lot of times things you've seen years ago, you weren't quite at the point where you could really appreciate what's going on. There's a lot of opportunities to advance, to push things further. And so over here, you've seen induction before. You've all seen how to prove things. Here's something interesting. Can you prove a formula by induction for sums of powers in terms of earlier sums of powers? What kind of tricks do we have? This is a really nice trick of, where is it? Of representing my number, the sum of k squared, breaking it up and saying which ones are the same, which ones are different. Okay. Now, of course, this leaves the natural question: how could you find the sum of k squared? So, again, this is a class where we have a lot of freedom. The things I had planned to talk about today was analyzing inequalities, induction, power sums, tilings, and Fibonacci numbers. If people are interested and want to talk a little bit further, we could try to talk about the fact that we actually don't know what the sum of k squared is. Do people want to talk about how could we try to figure that out in terms of what we already know? Yeah, I realized just a few moments ago that I hadn't plugged in my computer, and I was wondering if the battery would be enough to last. It loves defaulting when I don't check on it to putting the battery at use as much energy as possible. Even when I always tell it to, I have to always retell it that when I turn it on. Okay. All right. So anyways, do people want to go to other things, or do people want to spend more time and talk about sums of k squared? Either one is fine with me. We have freedom in a class like this. I'm sorry?
It's inequalities.
Inequalities. Anybody else have any preference? Okay, so let's start talking then about inequalities. And I'll leave as an exercise to see, can you think of elementary ways to try to find the sum of k squared? Or is that just a fundamental building block? All right, what is the most important inequality in all of mathematics?
A real number x squared is
good. So if x is real, then x squared is greater than or equal to 0. It is amazing how many things follow from this inequality. And then if you're going to do problem solving, if you're going to do math competitions, there's certain inequalities you need to know. Cauchy-Schwarz is one of them, generalizations, Holder-Jensen, whatnot. Geometric mean, arithmetic mean is another extremely important one. And so what I like about inequalities is for many problems, we don't need an exact answer. We just need to know ballpark what's going on. So if I give you two numbers, x1, well, let's do x and y, say positive numbers, they're greater than 0, and I want to calculate the mean. Can anybody give me a good definition of mean? So what should the mean of xy be?
Add them and divide by 2.
So one is, so mean is x plus y over 2. This is called the arithmetic mean. So as soon as you see that I'm putting a modifier in front of the word mean, it suggests that there might be other choices of mean. And as soon as there's choices of mean, you can start to ask which one is better. Well, better in what sense? So the question is, if I give you two numbers, I want a function, the mean function of x and y. And I want it to have certain properties. And we'll assume 0 less than x less than equal to y. Because without loss of generality, we might as well normalize so that y is not smaller than x. Can anybody tell me what properties you want? So if you're coming up with a mean function, what would the mean function have to satisfy for you to be willing to consider it?
Between x and y.
Okay. What's your definition of in between?
Like greater than or equal to x.
Okay, good. So x less than equal to mean of xy less than equal to y. And this collapses to the mean of x and x is x. Excellent. Any other property we want the mean to have? Okay, so good. We want symmetry. We want the mean of xy to be the mean of yx. And so you can start to ask, what properties do I want my mean function to have? And then is there more than one choice? So has everybody seen the factorial function? N factorial is n times n minus 1 all the way down to times 3 times 2 times 1. And we define 0 factorial to be 1. The factorial function is how many ways can we order n objects when order matters. There's a beautiful theorem. It's Bohr. No, I'm forgetting who did it with Bohr. I think Bohr and Molotov, I think. Yeah, where they proved that if you want a function that equals the factorial function at the integers and has a couple of additional properties, there's only one function that works. And it's the gamma function, if you've ever seen the gamma function in a probability, statistics, or number theory class. So what we are thinking about here is, are there any other properties we want to have of the mean? And you could start to ask, well, what if we wanted to find the mean for 3 things or 4 things or 5 things? Do you want maybe the mean of x, y, and the mean of wz, and take the mean of that to be the mean of, so you can start playing additional games like this. So I want you to consider the geometric mean, where the geometric mean of xy is the square root of xy, and the arithmetic mean of xy is x plus y over 2. So you can show very easily that both of these satisfy the 2 properties we said we want. They are both symmetric, and they both are between x and y with the endpoints included. And now we can compare. So let's compare the arithmetic mean of xy, which is x plus y over 2, versus the geometric mean of xy, which is the square root of xy. So one thing is to look at extreme cases. If x equals y, they both collapse to being the same. If y is much larger than x, so when y is very large relative to x, the arithmetic mean is approximately what? Approximately y over 2, and the geometric mean is approximately what? So this is where it gets a little bit tricky. It's not just the square root of y. You've actually got that factor of square root of x as well. So it's square root of y. If x is fixed, it's going to be of order square root of y. It's going to be much, much smaller than y. So looks like the arithmetic mean is greater than geometric mean for y much larger than x. Whenever you see a formula, you always want to try to get a sense of the scale, and you want to try to get a sense of, is there any normalization we can do? Without loss of generality, what does x equal? One. So this is a great point to be thinking about. We never mentioned this before. Here's a new property. Property 3. What should the mean of ax, ay equal? I'm sorry? It should be a times the mean of xy. So the mean of xy would actually just be x times the mean of 1 y divided by x. This is a really good property that a mean should have. If I rescale everything by 7, the mean should change by a factor of 7. And if you notice in all the equations, for the arithmetic mean, if I rescale everything by a, it rescales by a. If I rescale the geometric mean, I would have the square root of a squared xy. Oh, good. That's just going to be a times the square root of xy. So without loss of generality, we can always take x equals 1. This may not be useful. It may not be needed in this problem. But again, the point of this class is to try to emphasize techniques. Whenever you have this, what kind of symmetries can we get upon? We saw this when we were doing the integrals in Friday's class. Was this? No, this is Wednesday. We saw this when we took Monday's class and we did the integrals in Monday's class. That we were trying to get a sense of how does the integral depend on a and b when we had the exponential of ax minus the exponential of bx. And we eventually got it had to be the a minus b over ab. That was the one that had the correct parameter dependence. So now what we want to do is we have x plus y over 2 versus the square root of xy. If we wanted to, without loss of generality, we could assume x equals 1. So without loss of generality, x equals 1 is okay. So we would have 1 plus y over 2 versus square root of y. What is your first thought when you see this? So we're comparing 1 plus y over 2 versus the square root of y. What could we do to make the comparison easier? So what transformation could we do to both expressions to make them easier to compare? Square them. So we would have 1 plus 2y plus y squared over 4 versus y. If we bring y over, we get 1 minus 2y plus y squared over 4 versus 0. Well, this is just y minus 1 squared versus 0. The 4 doesn't matter. I can bring the 4 back over. And remember, y is greater than or equal to x, so y is greater than or equal to 1. So we know y minus 1 squared. This is the most important inequality in all of mathematics. So we know it has to be a greater than or equal to. And so we get the arithmetic mean of xy is greater than or equal to the geometric mean of xy. And again, there's a lot of great ideas here. We'll talk a little bit more about this in the next class, because there's more than just these two means. There's actually a lot more means that you've never seen. And it's good to be aware of them and good to be aware of how you get to the different analysis of stuff like this. All right, so let me stop the recording.